Good, great.
Okay, so
the floor is yours.
Thank you. Thank you again for inviting me to make this presentation as a sponsor. Thank you also to all the participants to attend this presentation. As you can see here, it's also a technical presentation that is mainly focused on the hole drilling measurement, and in particular on residual stress analysis by hole drilling. So I don't have so much time, so I will try to resume the main topics of this subject with some slides. So before starting, I will make just a quick presentation of myself. My name is Alessio Benincasa. I started in scene technology about 16 years ago. Scene Technology is an Italian company located in Florence that mainly works in the field of experimental measurements, and in particular, in this case, in residual stress analysis. And more or less, I have always been working in this field, in the residual stress field. That is the main subject of today. So what we are going to see today is mainly a brief presentation of residual stress, of the typical application fields and measuring methods, with a focus on the hole drilling measurements, which is a particular type of test when we have to measure residual stresses. In this case, we are also lucky because there is an international standard, ASTM 837, that regulates this type of test. So we will have a short focus on that, a short focus on our machine that we use for this type of measurement, with some typical examples and test results that will show a little bit what we can obtain, what we can reach with this type of test and machine. So maybe at least some of you, most of you, know the residual stress problem. Residual stress is something that we always have inside the materials, and the residual stresses is something that is present into the components, into the mechanical parts, even if we don't apply any external load. As a consequence, these residual stresses limit load capacity and the safety of mechanical components in operation. So in a few words, they reduce the lifetime of our parts. So it's very important to quantify the level of the residual stress that we have. There are several reasons for the residual stresses. Here we have reported the most important, the main ones. Generally, we don't have just one, but mainly a combination of some of them. You can imagine, for example, surface machining, surface treatment. So mechanical operation to give the final shape to our components, like turning, milling, but also surface treatment, like, for example, shot peening, that sometimes we introduce in our components. And of course, thermal effect, so very fast variation of temperature, so big temperature variation in short time, like solidification steps, but also welding, quenching. And also, for example, misfit among different parts in case of bulk components, like a bridge or a railway rail. But also not uniform plastic deformation during the process of material forming, material shaping, or chemical phase change, mainly connected with the polymeric materials that are also subjected to residual stress, of course. So there are several reasons. Generally, the residual stresses are self-balanced within the component. So we always have the equilibrium globally in the component. But on the other hand, we also have to take into account that the total stress that is experienced by a material in a given location at a given depth in the component is composed by two important contributions. So the total applied load are composed by the external load plus the residual stress, so the internal stresses that I have. This is very important because you can imagine, you probably can know the level of the external load that you are applying also with high precision due to simulations, experimental tests, experience. So there are several good possibilities to quantify the level of external load that you are applying. But if we want to completely characterize the material, we need also to quantify the level of residual stress, because the material has both the contributions. The material is not able to understand the difference between one of the two contributions. The material does not know if one is positive or negative or good or bad. So if we want to completely characterize the material, we need to know both the contributions. So the external stress, but also the internal residual stress that we have. And as a consequence for that, we have several different measuring methods. If we want to resume a little bit, we can divide them into three general types: mechanical, diffractive, and other methods. We will focus the mechanical relaxation methods today. Mechanical methods are really general methods, so they can be applied to almost all the materials. So this is a good advantage. They are not very expensive, but on the other hand, they involve the measurement of strain, deformation. And deformation is something that I can measure only if I remove some material. So in any case, we have to cut, we have to drill, we have to remove some material in order to generate some deformation that is then acquired and used in a special calculation software to finally calculate the residual stress. So there is a small damage. On the other hand, this is a very important method, very popular, because it is applicable to a lot of different materials. Also, diffractive methods are very important and popular because they are a sort of complementary method, as they don't need to be destructive if I want to limit the analysis at the surface. So if I cannot remove any material, then I can use the X-ray diffraction method, for example. X-ray diffraction is not very expensive compared with other diffractive method. But on the other hand, they measure only close to the surface. Otherwise, I have to remove the material as well. And then we have also other methods like magnetic, ultrasonic, that are not subject of this presentation as well. So we will mainly focus the first one. And among the mechanical relaxation methods, hole drilling is the most popular because it's probably the less expensive, fastest, and also the one that introduces the smallest damage. As you can see, it means making a very small hole, particular in some particular conditions, into the center of a special strain gauge rosette. So we install the sensor, the strain gauge, on the surface, and then we make this small hole, about 1-2 millimeters of diameter and 1 millimeter depth. And this hole is made in different steps, so that time by time we relax the material. We have some deformation that are acquired by the strain gauge. And then these deformations will be used to calculate the residual stresses with some special algorithms. And in this case, we are lucky, as we said, because we have a standard that gives us all the information to calculate the results. Another very important point for that is that with this technique, we can use the high-speed drilling technology. It means we can use a very special air turbine that rotates at very high speed, something like 300-400,000 RPM. And the big advantage in this case is that you don't add any residual stress into the material during the drilling process. So what you will measure is only the internal stress that is already present without inducing new ones. And as we said, this method involves some activities because we have to install a strain gauge. So if we want to resume in a few words the main activity for this test, we have to first install a strain gauge, then positioning the drilling machine into the center of the strain gauge, approach the surface and stop the system as soon as we touch the surface. It's a sort of the 0 point, starting point of the test, and then drill the hole. Drill the hole in different steps up to the final depth. And time by time, we will make the hole in several steps, and time by time, we will record the strain, the deformation that we have from the strain gauges. And then we will apply suitable calculation methods in order to build the stress state, in order to calculate the results. The final result is knowing the level of residual stress inside the material at the end of the test. As we said, I will just make a very quick overview because we don't have time enough. But in this case, we are lucky because we have an ASTM standard, ASTM 837. This is very popular worldwide. And this standard gives us all the information to perform a correct measurement and calculate the results with some information, limitations, suggestions, and so on. And basically, we will have the possibility to calculate the results in terms of uniform and not uniform stress field. So a sort of fast average calculation for uniform. So average stress value in the depth, and also more, let's say, accurate calculation that give us the real shape of the results, the real shape of the residual stresses over the depth that we have analyzed. So with the trend of the residual stresses in the depth. Also, just a very fast and quick overview of our machine for this type of test. We have the MTS 3000 is the system that we use for this measurement. It's a fully automatic machine that is composed by a mechanical part that realizes the hole into the material with very high precision, an electronic part that makes the test completely automatic, and then software for the setup of the test, for the acquisition of the values, and for the calculation of the results. So there is a sketch of the measurement chain that is very easy. So everything is connected together, mechanical, electronic parts, and computer, and compressed air in case we use the high-speed drilling with air turbine. That is the suggested option. But in case we don't have compressed air available, there is also the alternative option of electric motor, high-speed electric motor as well. So as we said, the test is automatic, so we can organize the test and have everything under control. As we said at the beginning, drilling, so total depth of analysis with different steps, strain gauge used, and time by time during the test, everything is under control, so we can visualize how things are going on. And then at the end of the test, everything will be calculated by the software. Just to give a very fast overview of how it works, you see there is a drilling part, and in real time, you have the possibility to see the relaxation trend during the test, as you can see here. Then here we have made things much faster than usual. But time by time, you will see that the drill bit goes into the material up to the final depth, and on the screen, you see the relaxation trend of the results. Okay, sorry, I stopped a little bit earlier, but just to give again a quick overview. So you see the drill bit that is going into the material time by time. And on the right side of the screen, you see the relaxation trend of the grids of the strain gauge up to the final depth, giving the final shape of the deformation that we have acquired. And these values will be then used in the calculation software. And before completing the presentation, just have a couple of examples of what we can obtain in terms of results after this test when we calculate them according to the ASTM standard. So this is an example in the aerospace industry. This is a titanium fuel tank, for example, very nice application where we had to measure the residual stresses in the welding area. So it's a very crucial area where usually the residual stresses are very high because there is a welding, as you know, but of course, there are also some suggestions to reduce the residual stresses a lot with some stress relieving process. And as you can see here is a typical result. You have the graph on the left of your screen, where we have on the x-axis the depth you have analyzed, and on the y-axis the principal stresses in terms of megapascal, red and blue lines that mean the maximum and minimum stresses, so the principal stresses at 90 degrees each other, as you probably know. And as you can see here, we have the trend of the residual stresses in the depth. And here we have very low values, despite we are on a welding, because it was stress relieved completely by the customer. And the results are, for example, less than 50 megapascal. On the other hand, opposite example, again, welding, this is a part of a pipeline with some welding in the middle, as you can imagine. And in this case, no attention was taken. So there was no process for relieving the stresses right after the welding process. So here we have the opposite situation. Again, we have the depth in the x-axis, principal stresses on the y-axis, with the red and blue lines. And in this case, you see that the results are about 10 times higher. So about 400 of megapascal. That is a very crucial and big value, also because it is tensile stress. This is typical trend of the residual stress in a welding area. We can have tensile stress in particular in one special direction, depending on the welding technique. And the residual stresses can be very dangerous and very high here, because of course, as we said at the beginning, if we consider the contribution also of the external load plus the residual stresses, this is a value that can be very dangerous for the customer. And finally, very final example, just to give a final idea. This is a oil and gas industry application. This is a turbine blade where, for the same reason, a shot peening process was applied. Shot peening, probably you know, is something that you introduce into the material if we want to add a compressive layer, valid in particular for the components that will be subjected to tensile stress during the lifetime in operation, in order to balance the tensile stress as an external load with the residual stress. In this case, we want to add compressive residual stresses. And this is a typical application. And if you check the residual stress here, as we did, you see again in the left side, a typical behavior of residual stress with compressive state close to the surface, with principal stresses that are very close to each other, with some hundred of megapascal, but in this case, compressive residual stress. That is good if we think that then this component will be subjected to an additional tensile stress in operation. So this was just to give another example and to complete also the presentation. Sorry for the so many information in just 15, 20 minutes, but I tried to give a very quick overview of this test, of this subject. So thank you again for attending this conference. Any question you can ask now, or you have contact details here also later if you have in the future. Thank you again.